Hello. There is a question for you. Please. As usual, you have two options. You can solve the problem, or you can check your luckiness for today. How's the sound? Good, thanks. Anybody need hot water? Also, okay. I found this an hour ago. It's not open now, so take it. It's yours if you want to. Yes. Sad day is closer and closer. I don't mean the exam, I mean the last lecture. One, two, three, so 100, 200, 300. Nobody pressed 0. Well, it can't be 0. The lowest possible temperature, that's impossible for these values. It could have been if volume was equal to 0, or pressure, theoretically. In real life, of course, that's not the case. And of course, all we have to do is write an equation. Which equation? Well, that comes with experience of solving problems. So my experience tells me this, which is based on the connections I'm looking for: pressure, volume, the number of moles, and temperature. These variables related by the ideal gas law. The question so far doesn't ask anything about heat or internal energy or change in the internal energy. So that's my best guess. And 20 kilopascals times 100 liters supposed to be equal to 20. This product, the whole product is 20. 20 divided by R by 8.31. That would give us the number of moles. We just don't really need it. Times T1. So the calculation tells us it's supposed to be 100. Well, now let's talk about the process. So that's the answer. Now, what if we're adding a heat to it, or changing something to the gas? Well, now we are adding an additional parameter, an additional variable. And now, so pressure, volume, temperature, and Q. Well, there is actually a direct connection between temperature change and the amount of heat. And we know that in general, we could have write an equation like this. It still works. Although for gases, instead of specific heat, we would use molar specific heat. But the thing is that for the gas, specific heat depends on the process. So not the best way to do it. We also know there's an indirect connection between heat, temperature change. That's the first law of thermodynamics. So that's what usually is the best approach to use the first law of thermodynamics. So you see, when we talk about heat related to solids or liquids, that would be the right way to do. But as long as we talk about gases, this is the best equation to use. Now, of course, we have to start adding. What else do we know? Well, first of all, before writing anything else, let's see what's happening. The gas expands at constant pressure. Okay, that's a very important fact. So the pressure remains constant and the volume increases. So this is the direction of this process from some initial volume number 1, which we know, 100 liters, to a new volume number 2. So P1, T1, V1, those are variables related to the initial state. P2, V2, T2, variables related to the final state. In general, P1, V1 should be equal to this times this times this. P2, V2 should be equal to this times this times this. We should check, just in case, did we add any amount of gas or it's been lost? Well, no. So the number of moles doesn't change, stays the same. And so two more equations. Well, I consider this as single equation. It just has two parts. And the second equation, it's not really an equation. Work is equal to area for this graph. The pressure as a function of volume. And now we start thinking, okay, what do we do first? Well, we never know, so we try. Trial and error. So because N, R, I are constants, the change in the internal energy is related to the change in the temperature. Well, that's how we calculate work for the isobaric process. Well, actually, monatomic, what does it mean? That's an additional piece of information. It's about that number we use for calculating internal energy, the number of degrees of freedom. So we can keep going. 3/2 times, well, this product equals 20 joules. Delta T, that's the temperature change, plus. Well, this is what I want to do. Delta V literally means final volume minus initial volume. So I can use this. Oops, wrong direction. Here, this equation minus that equation, because the pressure is the same, that constant. This gives me pressure times delta V, and R constant, common factor. This gives me delta T. So for the isobaric process, we also, I didn't finish. Oops, what did I do? So I have to finish plus work. For the isobaric process, we also can write that it's going to be equal to n r delta t when, well, delta t now becomes a common factor. So 3 divided by 2 times 20 plus another 20 times delta t. And the whole thing should be equal to this amount of heat. So that's the beginning of my equation, and that's the ending of my equation. And, well, so what does it give us? 20 divided by 2 is 10. Times 330 plus 2050. So 250 joules equals 50 times delta T. So delta T, the change equals 50 degrees. That's the change. But if we know the initial temperature, so now we're just adding the change to it, and that gives the final temperature. So the final temperature will be equal to the 100 plus 50, 150 kelvins. Every problem like that usually involves many, many connections of different type. So, but, well, we just have to believe it's doable and just walk through. Okay. More readable writing. Next question. All right. How much work has been done? Well, we actually have it found already. We just didn't use that number because, again, the work should be equal to this area, which is pressure times, well, again, this equation only works when the pressure remains constant. If it's not the case, this works always. And as we just said, that also is equal to again, and as we just said, that 20 times 50, 1,000 joules of work. And of course, the last question, again, just a straightforward application of the ideal gas law. The pressure is the same, so still 200 kilopascals. The volume, that's what we're looking for. This product is still the same, and the temperature has been calculated 150. So we can solve it. Meters cubed. Or take this number and divide by this. That will give you liters. It's handy to remember this conversion if you have to solve a problem with liters. Questions, please. All right. Well, we know what to do. Read, draw, write, solve. Again, it's physics, so we start from some kind of a visual representation. It doesn't make, of course, for this situation, drawing an actual gas. What helps is using a graph which indicates, which shows what is happening to this gas. So, constant pressure, okay, again, and the temperature is rising, which means volume is also increasing. So that's the direction of the process. First state. Second state, the process. State, another state. That's the volume number 1. That's the volume number 2. That's the pressure number 1. The pressure remains constant, so the pressure number 2 equals pressure number 1, 200 kilopascals, right? Tripling temperature, well, T2 should be 3 times T1. By transferring the certain amount of heat. So during this process, the gas absorbs 4,800 joules of heat. And the initial volume so again, which is handy because this factor cancels with kilopascals. Okay, and then, okay, we don't stop. Then we perform isochoric process. Well, we need to know the name. Isochoric means constant volume. So this, and the pressure increases, so we go up. That's the third state, P3, V3, T3. And the pressure doubles. So this pressure equals 2 times this pressure, which is 2 times this pressure because second equals first, which is actually, well, 400 kilopascals. And the V3 will be equal to V2 because that's an isochoric process. Find the total change, okay. So there is Q12, W12, delta U12. Those are amounts related to a process. The amount of heat transferred, the work done, the change in the internal energy. And of course, in general, we have Q23, W23, delta U23, that's a U. And of course, these quantities related by the first law of thermodynamics. So we can write Q12 equals delta U12 plus the work, yeah. Q23 equals, doesn't matter which term comes first, W or delta U? Of course not. 2 plus 3 equals 3 plus 2. Commutative rule works. And at this point, I don't even think about numbers. I don't know what I know or don't know what I'm looking for. I'm just throwing in all equations I can. Now, this work should be equal to this area. This work equals what? 0. There is no work done when the volume doesn't change, which makes it good. Well, simple number. Now, total change, of course, equals the sum of two numbers. Okay. So, delta U12 will be equal to this difference. This number is equal to 4,800. The work equals the area. So it has to be equal to pressure, 200 kilopascals, times the change in the volume, V2 minus 3 liters. If only we knew that second volume, done with this part. Well, what do we know? This is what we know. We know how temperature changes. That's an isothermal, isobaric process. So P1 V1 over T1 has to be equal to P2 V2 over T2. And the pressure is the same. Temperature is tripled. That means automatically the volume has to be tripled as well. So the volume number 2 has to be equal to 3 times the volume number 1, which gives 9 liters. So finally, 4,800 minus 200 times 9 minus 3, 6. So 4,800 minus 1,200, 3,600 joules. Well, the first part is done. Now we're going to talk about the next process. So this one, 2, 3. This volume equals 9 times 10 to the negative 3 cubic meters. This pressure equals 200 kilopascals, and this pressure equals 400 kilopascals. And delta U for this process has to be equal to I over 2 N R delta T. And as we know, well, let's write it once. Well, this is how can we rewrite it. And as we know, that should be well, in this situation, the volume is a common factor. It's a constant, so 9 times 10 to the negative 3rd. And here it should be 400 minus 200 kilopascals. So read. All right. So we're going to use this number. 3,600 joules is the change in the internal energy. $3,600 joules, that was the change in the internal energy, which also has to be equal to I over 2 P2 V2 minus P1 V1. That should be equal to I over 2 times. Now, the pressure is the same, is a common factor, so 200 kilopascals. And on the other hand, that should be equal to 9 minus 3 liters. So that should give I over 2 times 6 times 200. So I times, what, 600? So 3,600 divided by 600 equals I equals 6. That's a relief. Okay, it works. So we don't know what kind of a gas is that, but we were able to figure out that's a polyatomic gas. Well, and maybe CO2, we don't know. But now we can finish our calculation. So delta U23 equals 6 divided by 2 times 200 times 9. 6 times 9, 54. 100 joules, right? Well, okay. The last calculation is that total change equals 3600 joules plus 5400 joules. 9,000, right? Joules. What's the most important lesson from this problem? You gotta believe. That's it. Any questions? Well, now let's talk about a very, very important application of this particular theory, engines. Sir James Watt, and you know why the unit of power is Watt, because of him. He, well, we can say at the time perfected the steam engine, and that gave the rise to manufacturing, to the new way of transportation. That boosted the civilization greatly. So how does an engine work? Well, all we need is just lift. Let's hope it's hot enough. So we need to transfer thermal energy into mechanical energy. We want to make it move. So what do? Well, we can heat up the gas, and it does mechanical work right now. But if we keep heating it up, that's it. It's the only work done just lifting. So that's not an engine, actually. That's, well, lift. Yeah. Hydraulic press, for example. So what do we want to? We want to repeat this process again and again. How can we bring it back into the original state? Now we just have to cool it down. And of course, eventually, when it cools down, it goes back to this original state. But of course, we want to repeat this process. So what do we do again? This. And it goes again. And now what do? We bring it down to its original state. So we make a cycle. And every time, over each cycle, this device absorbs a certain amount of heat. Now, neglecting any loss of that amount of heat splits. Some part of that heat does work, which is good for us, and some other remaining amount of heat getting lost to the environment during the cooling process. That's it. That's how it works. So for any engine, we always can write the law of conservation of energy, not mechanical energy, yeah? General energy. Basically, first law of thermodynamics. This amount of heat getting split into work, and the rest goes back to the environment. Well, strictly speaking, it doesn't have to be this way. Yeah, we don't have to burn something always to get energy transferred from thermal into mechanical. All we need is temperature difference. We need a heater and a cooler. That's it. So instead of heating up, we can actually cool something down to bring the temperature much lower than the ambient temperature, than the room temperature. And in that situation, the temperature change should be sufficient Do you think it's water? Don't drink it. Where is it? Here. Okay. So it's going to take maybe a minute to kick in, so I'm going to switch to the slide. That's the law of conservation of energy. So if we're adding some heat into the system which is capable of doing some work, neglecting any loss to internal friction, for example. Yeah. This amount of heat splits into two parts: work, positive work done by the system on, well, piston, for example, and the rest goes to, well, the environment. So as we know, when the system releases heat, the actual value of that heat is negative. So we can rewrite this law differently. We can calculate the amount of work done as the difference between the amount of heat, I'm getting there, supplied to the system and the magnitude of the heat lost. Well, if you use actual values, you can write it like this. You just have to remember that's a negative number. And because an obvious relationship, the amount of work done always less than the amount of heat absorbed by the system. So we use this fraction as a measure of the efficiency of this engine. This is an official definition of the efficiency. Well, normally we would multiply by 100% just to make a number kind of nice. Any engine, of course, has efficiency less than 100%. If we can calculate it differently, like this, like this, like this. But more importantly, turns out, French physicist Carnot proved that if you have an engine which operates between two temperatures, this is what we call the temperature, the high temperature, the temperature of the heating system, heater, and that's the coldest temperature of the cooling system. In that case, an engine like that always has efficiency, well, ideally equal to, but in real life, less than this. So that's an official definition that works for every engine, actual numbers. This works for an ideal situation. And of course, in our problems, we usually treat any engine as an ideal. So we can use these equations together. For this engine, how can we calculate its maximum efficiency? Well, the temperature of the liquid nitrogen should be Tc. The room temperature should be Th. 1 minus Tc over Th. And we must use Kelvin. People forget about this very often. When calculating the absolute efficiency, you must use the absolute temperature, not Celsius, not Fahrenheit. Only absolute temperature works. Well, as we said, every engine every engine operates in cycles. So it repeats the same cycle again and again and again. It starts from some initial state, and then, well, there are many, many different cycles. This engine has a name, a Stirling engine. That's also a name of a physicist who developed it. It has a Stirling cycle. There's a Carnot cycle, Watt cycle, many different cycles. And for each cycle, you see, when volume expands, positive work is done. When volume contracts, negative work is done. So the total amount of work will be equal to the area of this cycle. If the cycle is, well, clockwise, system does positive work. So system actually does work we use for us. It's not an actual engine. That's more like a refrigerator. We do some work on the system, and that system pumps heat in a certain direction we like. Because we start and we end always at the same state, over the whole cycle, initial temperature and final temperature equal to each other, which means there is no change in the internal energy. So if we apply the first law of thermodynamics for the whole cycle, that's what we get. First example. Well, this problem is almost trivial, but let's do it. So what we know. Engine takes. Takes means, well, we always have to choose between two Qs. Absorbing, releasing, yeah, hot, cold. So if it takes heat, that QH, Q hot, now it does this much work. So first of all, if we want to, we can calculate how much heat is lost. It's just work minus this. This number is negative, of course. So what else can we calculate? The efficiency. The efficiency is just work divided by this. So again, times 100%. Done. What else can we calculate? Well, the lowest temperature. Again, when the question is about temperature, we have to choose between two. T, C, TH. TH at the highest temperature. TC, that's what we call cold, the lowest temperature. So that's what we know. That's what we're looking for. That's what we know. 27 Celsius. And now we have to remember, we cannot use Celsius. We have to use Kelvin. So it's 27 plus 273 divided by TH. Well, times 100%. So that's a very straightforward problem. A different situation happens when we actually have to use the information about the cycle to calculate stuff wherever we want to. So let's do this. Why is it important? It says it is not. Well, because if we were giving information about the Carnot cycle to calculate the efficiency, we could have used just this equation. We just need to know two temperatures. But if it's not the ideal cycle, that's it. We cannot use this equation. We have to actually start from calculating work, then calculating the amount of heat the system absorbs, and then divide two numbers. Well, what do we know? 200 kilopascals. 10 liters, 20 liters, 400 kilopascals. Well, now we can immediately see how we can calculate the work. It has to be equal to this area. So a rectangle, height times width, right? So, or times base. 20 liters minus 10 liters times 400 kilopascals minus 200 kilopascals. $20 minus 10, 10 liters. 400 minus 200, 200. Now, as we know, many times we've done it before, liters and kilos cancel each other out. So what's left is 10 times 200, 2,000 joules. Free energy. Now we need to calculate this thing. Again, not the total heat. We know the total heat of the whole cycle is supposed to be equal to the same number. We need to calculate the amount of heat it takes in. So strictly speaking, we have 4 Qs for this process, for this cycle. Q12, Q23, Q34, Q41. Some of these are positive, some of these are negative. So which positive, which negative? Well, if we don't know, we just have to calculate each one by one, and then just scratch off all negative Qs. They don't matter. So Q12 equals, well, delta U12 plus work 12. There is no work done for this particular process because the volume doesn't change. 0. That's delta U. So delta U, I over 2 N R delta T, or you see what we know, P's and V's. So what do? We jump from the temperature to pressure and volumes. First of all, this is a monatomic gas, maybe helium. So 3 over 2. 4, first of all, I already said first of all, so now second of all, the volume stays the same, 10. And all we need is the pressure difference. And kilopascals and liters getting canceled. So that gives us 400 minus 200, 200, 2 divided by 2, 100, 100 times 10,000, 3,000 joules. All right. Q23. That's an isobaric process. The pressure stays the same, work is done. So delta U23 plus W23 equals, well, we know what to do. Again, 3 divided by 2 times, if the pressure stays the same, That's a common factor. The same equation, but now the pressure remains the same. It's a common factor, and the volume changes. So the pressure equals 400 kilopascals, and the volume changes from 10 to 20. That's only the energy part. Now we have to add the work, which is, again, same pressure, which is 400 times same volume change. (20 minus 10). 10 times 400, 4,000. So this is 4,000, and we have 3 over 2 from the first term plus 1 from the second. So that's 5 seconds times 4,000. 4,000 divided by 2, 2,000. 2,000 times 5, 10,000. Now, Q3, 4 and Q4, 1 turns out to be both negative because they're opposite to these processes. If here volume is constant and pressure rises, the delta U is positive. That means here volume is constant and pressure decreases. Delta U has to be negative. Same here. So these two Q's are not the part of QH. So we're practically done. We just need to add two numbers. 3,000 from Q12, 10,000 from Q23. So 10 plus 3, 13,000. The work equals 2,000. So the efficiency will be work over total hot heat. 2,000 divided by 13 times 100%. Very inefficient engine. All right, let's write it down. So the efficiency will be work divided by hot Q, 2,000. Why is it so inefficient? A lot of heat gets lost to the environment. And 10,000 plus 3,000 and times 100%. That's it. So the last part, of course, is the least important part of this problem. The most important part is analyzing a cycle. Analyzing a cycle. Well, I'm going to try one more. Come on. Oh, come on. Come back. Come back. Come back. Come back. A cycle like that. Well, the ideology, the strategy is absolutely the same. Still, we have Q31, which is positive, Q12, which is positive. So QH will be equal to Q31 plus Q12. Q31 will be equal to delta U31 plus 0. There is no work done for this process. So I over 2, I equals 5 times P1 V1 minus P3 V3 plus 0. Q12 equals delta U12 plus work 12 equals I over 2 P2 V2 minus P1 V1 plus the work. Constant pressure means P1 times V2 minus V1. And we know what we know. We know this. And we know this. Okay. There's one more thing for this problem to be added. Here, it's very important this has nothing to do to physics, pure geometry. This line is a straight line. So if I want to calculate the slope, P3 over V3 is supposed to be equal to P2 over V2. This, again, has nothing to do to physics, pure geometry. And that equation gives you the third volume missing. You see, you know everything, and you can solve for everything. The area of this triangle gives you work. And now we're done with this. I've got a little bit more stuff left, but not the new stuff, basically. Just a couple of more examples, a couple of more demonstrations. I may have some extra time left on Wednesday for your questions. We'll see. So just in case, prepare your questions. See how long it works. It's because the temperature difference is very large. Larger than this. This temperature difference is about 80 degrees. This is more than 100. And now, no temperature difference. It stops. Don't forget the sign-in sheet right here. Yes.
Just really quick.
Yep.
Why can you neglect 3 to 2?
What do you mean?
Like you didn't calculate, like you left out the Q of 3 to 2. Is it equal to?
No. From 2 to 3, Q will be negative.
Yeah. So why wouldn't you count it into the total Q?
There is no total Q. The efficiency equals the work done divided by Q absorbed by the system. Oh, thanks. So this has to be only positive Qs, you know. That's why I don't really care about negative Qs.
But what if the gas, like what if the direction was?
If you have a cycle,
Yeah, so like there's no.
doesn't matter. If you have a cycle, you must have certain positive Qs and certain negative Qs.
Yeah.
Otherwise, it's impossible.
But how would we know the direction of the cycle?
Well, it always goes from 1 to 2 to 3 to 4 to 5. It goes in direction of the increasing numbers. The first state is number 1. The second state is number 2.
Okay. Thank you.
Sometimes, instead of numbers, you might see an arrow. Yeah, like
That's how it is in the homework.
Maybe. Yes.
I is the Van Tal factor. I. What's I?
It's a division.
Which I? The little I.
Yeah, the little I. Yeah.
This I.
Is that the number of like atoms? Like
No, it's not the number of atoms. It's a number of degrees of freedoms of that atom or molecule.
In this case, would it be 2 or
because if it's a diatomic gas, then, like I don't know how you're supposed to calculate it.
it's just 1 minus whatever you have?
Memorize. Monatomic gas, I equals 3. Diatomic gas, I equals 5. Everything else, I equals 6.
Okay.
That's it.
3, 5, and 6.
Yes, 3, 5, 6. Okay, so. All right. Okay. I guess that's it. I'll bring the rest.